Hello students, welcome to lecture 2 of the ongoing chapter Systems of Variable Composition. In this lecture, we will try to understand what is chemical potential. We will see the chemical potential of a pure ideal gas, and we will also try to determine the dependence of thermodynamic parameters on a composition. Now, when a reaction proceeds, whenever there is a chemical reaction, there is change in not just the composition of the system but also the thermodynamic properties. Now broadly, thermodynamic properties can be divided into extensive and intensive properties. Now one of the most fundamental equation of Gibbs energy is dG equal to minus S dt plus V dP. Now how does equation come into being? We know that G is equal to H minus Ts. This H, enthalpy, can be written in terms of internal energy plus PV, and you repeat this term minus Ts. Now if we take dG, the value will be du plus pdV plus vdP minus tds minus s dt. Okay, now we know since du is equal to tds minus pdv, so this is pdv, this is tds, therefore dg is equal to du minus du plus vdp minus sdt. This will cancel out and we will get this form of the equation where dG is equal to minus S dt plus Vdp. This equation holds true for a constant composition. If the number of moles, say N1, N2, N3 of the substances present vary, then G not only varies on these terms but also on the number of moles present. So we can write dG is, we have already seen this equation in the previous lecture, dG is equal to dG by dt at constant pressure and composition into dt, plus this equation continues. Okay. Now suppose if there is no change in composition, then the equation 1 becomes dG is equal to del G by del T at constant pressure and composition dt plus del G by del P at constant temperature and composition dP. Now if we compare this with the fundamental equation, we see that this value del G by del T at constant pressure and number of moles becomes equal to minus S, and del G by del P at constant temperature and composition becomes equal to V. Now we introduce a term mu such that it is equal to change in Gibbs free energy with respect to change in composition. So del G by del Ni is equal to mu Ni at constant temperature, pressure and Nj where I is not equal to J. Now from the previous equation, that is from equation 1, this equation, we write dG is equal to minus S dt from here plus vdp plus mu1 dn1 plus mu2 dn2 plus it continues until mu n d n n. So what is chemical potential? Chemical potential is defined as the rate of change of free energy of a thermodynamic system with respect to change in the number of atoms or molecules of the species that are added to the system. So it is the partial derivative of free energy with respect to the amount of species where all other species concentration is constant. Okay. So chemical potential of the ith component is a state function, and it defines Gibbs energy and other thermodynamic potentials when the number of particles of a corresponding component is changed. Also, the ith component of the system has chemical potential, which is the derivative of any thermodynamic potential divided by the quantity. In other words, it is a measure of how much free energy or free enthalpy of a system changes if we add or remove d and I particles of the species I while keeping the other particles concentration and temperature and pressure constant. So, chemical potential can also give the condition for thermodynamic equilibrium. But how? When the sum of the product of chemical potential and stoichiometric coefficient for all reagent is 0, then this equality condition is that of a chemical equilibrium. What are the units of chemical potential? Since it is expressed in terms of energy per unit substance, so the unit is joule per kg or joule per mole. Let us try to understand. Suppose there is a substance, okay? That substance has a tendency to react with other substances or to undergo physical change or phase change or to reorganize and rearrange in space. Now, how much this substance has a tendency to do these things can be expressed in terms of chemical potential. So, if the numerical value of mu is high, then the magnitude of undergoing such changes is high. It is determined by nature of the substance as well as its system environment. Okay? Suppose there is a transformation from solid liquid gas. This will be more pronounced if the tendency for the process in the initial state has more, a tendency to change than in the final state. So, the chemical potential is a measure of the magnitude of this tendency. When we write mu A, it signifies the potential of the substance A, and greater the value of mu, the more active mu is. Okay? So, chemical potential is determined by chemical composition and characterized by empirical molecular formula and also by the state of aggregation and crystalline structure. For a pure ideal gas, chemical potential is given by this equation. We see that at a given temperature, it varies with pressure. So, if matter flows from high pressure region to low pressure region until the pressure is equal throughout the vessel, the equilibrium condition, equality of chemical potential everywhere, requires that pressure to be uniform throughout the vessel. What will happen in terms of a non-ideal gas? This pressure term will be replaced by fugacity term. What is the dependence of thermodynamic parameters on composition? Here we have written the thermodynamic parameters internal energy, enthalpy and Helmholtz free energy in terms of G, and we have taken the derivative du, dh and dA, and this is how we expand the equation. Now when we substitute the value of dg from what we have obtained, that is Tds minus Pdv plus summation of mu I dni gives the value of du. Similarly, if we replace the value of dg in the other values for dh and da, we get the dependence of thermodynamic parameters on the composition in terms of chemical potential. So finally, we can conclude that this value mu I is not just the change in Gibbs free energy with respect to change in number of moles, but also can be given as change in internal energy with respect to change in number of moles, or change in enthalpy with respect to change in number of moles, or change in Helmholtz free energy with respect to change in number of moles, where the other terms are kept constant. So with this we conclude today's lecture. Thank you.